Up to now, I was talking about some kind of elementary differential geometry, and things were sort of defined by some axioms and things like that. And today, I want to talk a little bit about the meaning of all that stuff. So it will be slightly more physicsy in some sense, but not too much. So let's call it the meaning of all that. So what we were studying was that we had some kind of a general Courant algebroid, and inside a generalized metric. And what it gives us, this kind of pair, well, the Courant algebroid itself gives us at least some kind of formally, a three-dimensional topological field theory, which is called Courant sigma model. So it will be maybe I can add E to that. It's that Courant algebra that we're using. We already heard about it several times, but at least people who are here. So I will not say any details about it, but let me just say that a particular case is Chern-Simons theory. So in the case of E is a point, so E is a Lie algebra, so when this is over just a point, how is it? M, that's equal to a point. So this guy is simply Chern-Simons with the action functional, which is like one half ADA plus 1/6 A, and this guy is A. Okay, this is an integral over some three-dimensional thingy. So yeah, my handwriting is not optimal, but anyway. So this Y is our three-dimensional manifold over which we're doing it, and A. Let's forget about non-trivial bundles. Let's just imagine it's a one form with values in G, or more properly, since things are going to be in Bata and Wilkowicki formalism just in a second, so more properly, this thing should be rather replaced by omega YG shifted by 1. So this is really only the degree 0 part of the thing, which contains also, this contains also the ghost and anti-fields. Okay, so far for E, it gives us this nice topological thing. And what does V plus does for us? It gives us a boundary condition. So it is a boundary condition for this topological thing. And the interesting thing about this is that this boundary condition is not topological. This is like a true dynamical thingy with local dynamics. This guy is non-topological. So if you wish, we can call it equally well a boundary field theory. It would be a fitting name for that. And as I told you, at least now, I will not write what in general this E-Courant algebroid, this Courant sigma model means, but it's not so important. But what is happening in the case of an exact Courant algebroid? So if E is exact, then modulo as a tiny lie, but which is not important, this topological thing here is actually trivial. There is nothing happening in that Y. One can just get rid of all those fields, all of them are kind of auxiliary. So this topological field theory becomes a true field theory which can live on its own. It doesn't need to live on the boundary of anything. So the E Courant model is trivial. And so we get an ordinary two-dimensional field theory. And what is that field theory? It's the two-dimensional sigma model, as it should be, right? If you have an exact Courant algebroid and a generalized metric, this is what gives us a sigma model. Now, okay, what was that little lie? As I said, for this two-dimensional sigma model, we have there, we had somehow metric and the closed tree form. And to make sense of it, really, in the two-dimensional sense, this closed tree form needs to be upgraded to a differential character. So it's like its periods have to be integral and things like that. So it's only in that case when we can completely get rid of this interior. Otherwise, it's basically, the statement is that this Courant sigma model is equivalent to like a silly Lagrangian, which is given simply by integral of that closed tree form. Okay, I don't know whether it makes sense, but this is somehow what's happening. So in general case, the thing is a boundary field theory. In the exact case, it is the topological thing is equivalent to a trivial thingy, and so we can see it as a just two-dimensional field theory, which is not on the boundary of anything.
There is a question?
You don't believe me. Very good.
No, I don't know. I just wanted to know more precisely what are these conditions you put on H. So H is not just exact, you say, so that it really becomes a 2D field theory.
Okay. Yeah.
So normally it should be West-Zumino term, I suppose.
Yeah, yeah. Okay. Now here I meant in the sense, like if you want to define a e power I s, if this is supposed to make sense, so then S doesn't need to be really like totally independent of what's going inside. But so then what one needs to do is one needs to turn H into a differential character. In particular, it means that the periods of H don't have to be 0, but they have to be integers, or 2 pi times integers.
And what is the definition
of a differential character?
Right.
It's a thing which assigns to any 2-cycle okay, it's enough if it assigns a number like a thing in U1, a complex number with modulus 1, and such that there is also a closed tree form with a property that if the cycle is actually boundary of something, then this guy can be obtained by exponential of I times integral of that tree form over the interior or something like that.
But the tree form can change in each case.
The tree form is, yeah, good. Okay, anyway, so that's the definition of differential character. But it's, okay, it's not important, as I said.
Pavol, and this is, I guess, it's here. This is, I guess, for bosonic string theory, right? Or there is a generalization for type 2 or for heterotic?
This is one of my open problems for the end of this talk.
Mm-hmm.
Yeah. So the thing that is, anyway, so what we're getting out of this when E is exact is just an ordinary two-dimensional sigma model given simply by G and B or G and H. There is nothing else. So if you want to get some kind of supersymmetric like two-dimensional thingy, two-dimensional model, then all this story needs to be modified, and I don't know exactly how.
I guess the same for heterotic sigma models, right?
Yeah, anything which would contain any like any fermions.
Mm-hmm.
Yeah.
And gauged two-dimensional sigma models?
For gauge, it's not so bad. There is some famous paper that we wrote together, I guess, at some point. Yeah, one can slightly extend this notion of a generalized metric to be some kind of crossover between a Dirac structure and a generalized metric, something in between, and then it will be like the resulting thingy will be like a gauge theory, gauge two-dimensional theory. Okay. So this is a general picture, this stuff. And let me now tell you in detail what's happening in the case of Chern-Simons theory, like when it's over a point, because then it's the simplest case, but it also contains basically everything that one needs to understand. So what is the statement? Okay, the case of M is a point, and therefore our Courant algebroid is just a Lie algebra with inner product. And now we have our generalized metric, which splits it like that, and we should consider Chern-Simons with this thing. So from that, we're supposed to get some boundary condition, BC boundary condition for Chern-Simons. And now when it comes to boundary conditions for Chern-Simons, there is the first one and the most important one probably that comes to mind, which is the chiral boundary condition. And this is not the one that we're going to use here, but it's basically the same thing. So a little reminder, or whatever reminder that the chiral boundary condition of Chern-Simons is simply, okay, so we have our, how does it work? So we have our three-dimensional manifold, and then we take its boundary, and we need to choose a complex structure or conformal structure on sigma. So the boundary condition actually uses this conformal structure. So this guy is now a Riemann surface. And the boundary condition says that when you take the field and restrict it to the boundary, then A somehow on the boundary should be in omega 1, 0. It should be a 1, 0 form on sigma with values in G. And if you're talking about this in this BV language, then there might be also a two-form part. So omega 2 sigma G. The fact that there is no zero form part, it corresponds to the fact that there are no gauge transformations anymore. It's like zero forms are ghosts. So we just declare there are no ghosts, which corresponds to the fact that this boundary condition kills a gauge symmetry on the boundary. Just some kind of statement. The two-form part just has to be there. If you don't have the zero-form part, and the boundary condition needs to be somewhere like a DG Lagrangian something in the space of boundary fields, then to compensate for the fact that there are no zero forms, we need to put there all two forms. It's just like formalism. And this, by the way, corresponds to, this is what is used in the case, the only reasonable case probably, when G is a compact simple Lie group, where like this Chern-Simons really makes sense. And in that case, the inner product is the one which is given by the trace, and it's negative definite. Negative definite. So, yeah, that's roughly what's happening here. Now, we're going to use it for G, which is where this inner product is not negative definite, where it has both some plus part and some minus part in the inner product. So then Chern-Simons, I don't know whether it makes sense non-perturbatively. Maybe, hopefully, in some cases, yeah. But for me, everything is going to happen just as a perturbative field theory. So our boundary condition is a straightforward generalization. So let's call it definition. The V plus boundary condition is simply given by same looking thing that now we have omega 0, 1, sigma with V plus, plus omega 1, 0, sigma V minus, and any two form. So this corresponds to the fact, as is negative definite, when V minus is everything and V plus is 0, if you want to really compare those two things. Okay, that's our boundary condition. So let's say, classically, the way it's written, it is, let's say, conformally invariant, in the sense that it uses just conformal structure on sigma. It doesn't use any Riemannian metric or anything like that. But if you try to do perturbative quantization, then things start depending on the cutoff, and it might easily happen that the thing will no longer be conformally invariant. That's really the story that this is somehow about. Like finding the condition for when this boundary condition actually is conformally invariant, even after quantization. And yeah, we can do it up to one loop, and then like some smarter people should do it for all loops or something. Okay, maybe a little bit, so how it fits to this Poisson's T-duality. I never properly defined Poisson's T-duality. I'm not going to do it, but still, let me. Let me say at least something about it. So, as I said, this is a boundary condition for Chern-Simons, or boundary field theory, if you wish. It doesn't live on its own. It doesn't. It needs not just sigma, but also some interior. It needs something three-dimensional. But how can one get rid of that three-dimensional thing in one possible way? So let's take three-dimensional manifold, which is just sigma times an interval. So it looks like this kind of slab. So that's I. And let me now put this V plus boundary condition on one side. And here I will put okay, that's where the dynamics is happening, that is this non-topological thing, but here I will put a topological boundary condition, so no local dynamics. So here I will use a Lagrangian Lie algebra in G, and I will say that A restricted to sigma should have values in this guy. So in sigma, comma, H. That's a topological boundary condition, at least classically. Again, after quantization, there is some tiny problem when H is not unimodular, but let's forget these kind of problems. So this is a topological boundary condition. This is a dynamical boundary condition. And the entire picture looks now as a field theory on sigma. Though I know there are like very many fields because they depend arbitrarily on this coordinate on I. But it is a thing which is on sigma. And yes, this is in the end isomorphic. One can get rid of those fields inside. This is isomorphic to A or V to the sigma model with target G mod H. So see, so somehow we get rid of that interior by putting there another boundary condition, but this time a topological one, so no longer any dynamics. And now what is duality here? So the duality was that if we choose a different H, then we get Well, not the same thing. Where the target space is different, definitely, but also the picture is not quite the same because there is a different boundary condition, but at least we can say that those two things, those two models differ only by topological degrees of freedom. All the dynamical degrees of freedom are the same. They are happening here. This is not touched. This is not changed. This interior is not changed. It's only this topological boundary condition which is changed. So it's some kind of, one can say that those two models, they are obtained one from the other by some kind of topological twist, whatever that means. It just means that we change somehow some topological degrees of freedom. Okay, so this Poissonian T-duality is not what is normally called duality in string theory or wherever, where one really wants to have a true isomorphism. Is everything okay? Or no? No. Okay, so it seems to be okay. Okay, thanks. Okay, so what happened, as I said, so this is not a true isomorphism. There is some topological difference between those two models. If you have like G mod H and G mod H tilde, and here there might be H or H tilde in G. These are not quite the same, but let me just say it in words. What's happening for ordinary T-duality? So for ordinary so-called abelian T-duality, the one which really works, all the corresponding groups or the algebras are abelian, but one also needs to talk about groups really. So the groups are tori, abelian, definitely abelian groups. And what happens is that classically this topological boundary condition, it does depend on the choice of this Lagrangian Lie subalgebra, or this Lagrangian subtorus. But when things are set up properly, meaning that H bar is equal to 1 and I don't know what, so in that case, those classical boundary conditions actually coincide after quantization. So things somehow conspire in such a way. Yeah, and that is, okay, this is not a very usual point of view of T-duality by saying that that's what happened, but at least for those, this abelian case, abelian, Chern-Simons, and boundary conditions, I can cite an authority, which is Kapustin and Saurina. There's a paper which discusses boundary conditions for abelian Chern-Simons. And in the simplest case, all boundary conditions just coincide on quantum level. And that's what we need. Okay, so this might give some explanations for what is going on and what might be going on. There is not a single non-abelian G where I could tell you that those two classically different boundary conditions actually coincide after quantization, or not yet, maybe one day, I don't know. This is what it is.
And this paper of Kapustin and co-author, does it discuss T-duality in
this
context?
It's a topological field theory paper, so in principle it's like very simple.
But if one applies it to T-duality, it reproduces T-duality with this idea?
Yeah, if you just take this sandwich picture where you're putting those two boundary conditions, and yeah, it reproduces T-duality. Okay, so that's far for the fairy tales. And now let me talk about, I should apologize to some people that probably to people who are funding this thing, or to organizers, that there is a big overlap between this talk and a talk that I give in kind of still the same program, but online. So I hope that you don't mind, and I hope that there are people who are not present for this online thing. So. But I thought that it would just fit very well to this like to this mini course. So let me now do some simple perturbative calculations with this V plus boundary condition. So this is all some kind of fairy tale. So now perturbative calculation with this V plus boundary condition. And on what I will, for my Y, I will take simply a three-dimensional ball. So Y is going to be just three-dimensional ball, so sigma, that's the boundary, is just S2. And for the complex structure, we just take the standard one. Let's see, this is CP1. And we're going to just see whether, check whether this classically conformal boundary condition, whether it stays after, say, one loop calculation, whether it stays conformal or whether there is some cutoff dependence, and whether we get like this renormalization group flow and things like that. So we'll reconstruct at least a bit of what happened before, but not everything, unfortunately. So this we actually did recently. So there's a joint paper with Jan Pullman, then me and Donald Humans. Right, so what does one need? So what we actually need to do the perturbative calculation, we need a propagator. That's the first thing. And the propagator, things should somehow depend on that G, I don't know where it is now, on G and V plus and V minus. But these things enter the propagator only in a super mild way. So the propagator actually doesn't care about any Lie algebra, really. So we can start with the case propagator of Chern-Simons theory on a three-dimensional ball with V plus boundary condition. But in the case, so the first case is when G is just one-dimensional. So basically, there is no G. We just suppress G, and also it's just V plus is equal to G, meaning that V minus is equal to 0. So what is the space of fields? I will just write down the boundary condition. So like all boundary fields are all forms on S2 just with values in this thing. So I'll suppress writing this Lie algebra. Now the boundary condition is that we don't take all these fields, but only one. Sorry, no, this should be V minus and V plus should be 0. So 1, 0 forms plus 2 forms. Yeah, and then we take off the forms on B3 with this boundary condition. So how is it? So here we have omega B3. And finally, our space of fields is those forms whose boundary values are here, right? So omega, there is a stupid notation that omega B, like forms that satisfy the boundary condition. B3 are those that are here. Okay, very cool. So that's our space of fields, and the propagator should be a contracting homotopy for this complex. Like in Chern-Simons theory, or in AKS theory, or anywhere. I will write it down. So the propagator should be a map of degree -1, h going from omega b3 to itself, such that dh plus hd is the identity. Now, okay, if one goes through the rules of BV quantization, what does one needs to pick a whatever Lagrangian submanifold in the space of all fields and integrate only over that. But finally, what it boils down to, that it's like in this case, it should be like a complement to closed forms. So there are closed forms, then one should choose a complement to that in the space of all forms. And so finally what it is that it gives us precisely this kind of homotopy. So D is going to give us an isomorphism between, that complement and those closed forms. So D goes like that. And we want it to be really an isomorphism if we want like this quadratic thing to be invertible and things like that. So, and finally, one can even forget about all this BV nonsense. I mean, this choice of Lagrangian submanifold and things like that. Finally, all that is important is a choice of a contracting homotopy. It doesn't have to come from this kind of splitting. It can be anything. Okay, very good. It's like a...
You are now muted.
Was it the singularity or?
You are now unmuted.
Yeah. Oh, yeah. Okay, yeah, you're right. So if you, it comes from the kinetic term, but where with this BV thingy, this H is sort of inverse to D, like this sort of inverse as it's written. Okay. Right, so we need this. It should be given by some nice integral kernel. So given H given by a nice, whatever it means, integral kernel, which I will call P0. So that's now stands P for propagator. This integral kernel, which it's a two form on the space of pairs of points it's like on B3 times B3, but minus diagonal. So it's what is called the configuration space of conf2 of B3. And basically what it should satisfy is that if you want to have that thing, then D of P0, once we understand P0 really as a distributional form on B3 times B3, so if you include the diagonal back, so it's like a form which has singularity along the diagonal. So I will write it in slightly in quotation marks, so that D of that should be the delta current, which is on the diagonal B3. So this form is really closed. But when somehow formally, when we allow those points to collide, it should not, this distributional D should produce this kind of thing. But what it really means that if we like integrate P0 along some sphere which is around the diagonal, the result should be 1. Anyway, so something should be 1, should be equal to 1. Sorry. Okay, so that's it. So that's what we're looking for. And now it was reasonably clear, and then this thing. I mean, A is given by. Sorry, what is H? So you just take a form on in this thingy on B3, then you multiply it with P0. So it is a form on B3. This is a form on B3 times B3, and then you integrate over B3, sort of. I hope you understand what I mean. And so this is this H of alpha. And then when one writes what it means, like dh plus hd of alpha, it really means that we are only taking d of that p0. And you see this delta is the kernel of the identity. Oh, okay. Okay, and it took us, I don't know, it's probably like trivial to find such a solution, but it took us a few months to find it, but so I can tell you what it is. So now just some random formula. So the thing is that there is a two-form.
But it should be also like Chern-Simons theory, should be known in some way.
Like Chern-Simons with a chiral boundary condition, I would think that everything should be known. Also perturbatively, even though of course it started non-perturbatively, but so many people studied Chern-Simons perturbatively. Just my Googling skills failed me, but I still expect that it's somewhere. So if the big blue button knows where it is, then please tell me. Anyway, so let me just write some, it's like formulas, so let me now enjoy those formulas. So it's we start with a two-form, but which is for the configurations on the boundary. So it's on conf 2 of whatever, CP1. That's our boundary sphere. I will write it down in coordinates. So on CP1 we have coordinates Z, so we have like Z1 and Z2. And the form is dz1, which dz2 divided by Z1 minus Z2 squared. But once again, I can give you this nice exercise that find a direct definition that doesn't use any coordinates and show in that way that this form is actually SL2C invariant. It seems to be, okay, it's written in coordinates, but it's actually something completely natural. So yeah, certainly at least it's a closed two form. So far, so good. But then we want to have a form which is here.
Why SL2C invariant?
Once you solve this exercise, defining it somehow geometrically, then it will be like invariant with respect to all automorphisms of the structure. So with respect to all automorphisms of CP1, that's SL2C. So you'll see it. But one can also just plug in an element of SL2C, like do a fractional linear transformation and see directly that it is invariant. It's also like easy calculation. Okay, so how to go from here to there? So that's somehow our ball with a boundary. Now we take 2 points inside, so points Q1 and Q2. That's a pair of points in B3. And then we take the hyperbolic geodesic, so connecting these 2 points. The hyperbolic geodesic, it will end on the boundary, and let's call it Z1 and Z2. So let's say that we map Q1 and Q2 to Z1 and Z2. And let's call this map R. It's a map which goes from this configuration space to that configuration space, and the propagator is simply R star of omega, times 1 over 2 pi I, or whatever, for these normalization purposes. That's the propagator. Maybe like to make some sense of it, so I don't know anything about physics, but you do, so you would, forgetting those dz's, you would recognize these as correlation functions of two currents, just whatever, abelian, like in free conformal field theory, so if you take, that's something that's happening there, and we should really be getting these kind of things when we're on the boundary, and then somehow we pull it back to this ball, and horribly. No, it's never needed, this kind of expression. It's given by the picture. I don't know. Yeah, okay. It looks some, I don't know. Okay, very well. And now let me restore back the general case, the case of arbitrary v plus and v minus. This was for the case when like, things were simple. So now, in this case, so we're going to get propagator, which is just like this thing for v minus and the complex conjugate for v plus, roughly speaking. The propagator is sorry, p, which is like okay, where it is. So p is in A2 form on the configuration space, B3, but with values in G tensor G. And it is P0 bar tensor, now the inner product, or sorry, the pairing, if I put it like that. So it's this thing is in V plus tensor V plus, or it belongs to, and it's the pairing on V plus, restricted to V plus. And then there is the second part, which is P0 without bar, and times the same thing on V minus. Just this. Okay, that's the most difficult part for setting up the perturbation like expansion. Once we have it, we just start drawing Chern-Simons diagrams and see whether there are any divergences. Interestingly, or not so surprisingly, there would be divergences, but happening on the boundary, because it's the boundary condition that's not topological. But inside, there wouldn't be any divergences. It's topological field theory. There's sorry?
Yeah, could you please remind us what T plus and T minus are?
What it is, or yes. What is T plus and T minus? Yes, so T plus is in V plus tensor of V plus, and it's the inverse of the pairing when restricted to V plus. So T plus plus T minus is the inverse of the pairing on entire G. Thank you very much. Okay, so let me now draw things just schematically. It's not really necessary to see detail. So diagrams in Chern-Simons theory, they are given by trivalent graphs, things like that. Maybe with some univalent things where we would be putting sources or external fields if needed. And on the vertices, we put the structure constants of our Lie algebra. On each edge, we would put the propagator, and then finally we would just contract things so to get just a differential form, and then integrate over all possible positions of these points inside B3, roughly speaking. So that's what a Feynman diagram looks like. But now this P is written as a sum of two contributions. So we write this P plus P minus, because as usual, we want to now separate the expression for the diagram into just pure integral and pure Lie thing. So a thing which is happening just in Lie algebra, where we contract indices and get some combinatorial expression, and the other thing should be just a pure integration independent of any G, V plus, V minus, don't know what. Does it make sense? So if you split it like that, then this thing becomes really a sum of things. Okay, the same diagram, but where we're now putting all possible signs, like plus, plus, minus, or things like that. I was, maybe before I was really denoting it. Let me denote it the same way. Like.
May I ask, like the principle? So you look at all one-loop diagrams, or what?
You look at, now we should look at all diagrams. So yes, I'm not reminding you because maybe I'm not really the expert on that, the rules of perturbative quantum field theory, but well, just to get whatever correlation functions, or here there are correlation forms really. One should take the sum over all diagrams with given external legs, and over all possible graphs, and then multiply it also by h power the number of loops in the graph, and things like that.
And on the one-loop level, there would be, there could be like many more vertices, right? You could add a lot of them.
This is just so, one particular diagram, which turned out to be one loop.
Yeah.
Because which I drew randomly.
But for this anomaly freedom or the conformal invariance, you look just at what precisely?
Yeah, we're getting there. So we write it this way, and now these diagrams, each of them can be written down as an integral, which doesn't care about any Lie algebra, V plus or V minus, where we just put, say, P0 bar here, P0 bar here, and P0 there, and integrate. Yeah, that's it. And for the other thing, we would be now putting like this Lie thing, where we would be putting those orthogonal projection to V plus or V minus, and yeah, so things now nicely separate. And so now the statement is that there is only one divergent one-loop diagram. So when we stay with one loop, so only the only divergent one-loop diagram is this one. And the external things, okay, I'll put there also those external things, plus and minus. So this is the only thing, the only diagram that diverges. Now, it requires a little bit of looking into those integrals. But yeah, so there is like a simple scaling argument for why like a diagram with at least 3 external things would converge. It's just there's there's some power which is decreasing fast enough, something. And when there are 2 outgoing thingies, then okay, you see we cannot have plus and plus because like P0 bar times P0 bar is just equal to 0. The form is of that sort, so it has to be plus and minus. And with a bit of like staring at it, one can also see that these two signs also have to be opposite if you want to have divergence. Okay, I should probably come to or start getting to the end. So at least what we see here, we see that, let's say, the condition for one loop conformality, if you want this boundary condition to stay conformally invariant, or independent of any cutoff, so that, or finite. I haven't talked about cutoffs yet, but if you want this thing to be really finite, then the condition is the vanishing of this diagram seen as a Lie thing, because it's a product of 2 things. One is integral, which diverges, but if it's multiplied by 0, then it's fine. It just drops. Okay, so conformality condition is that this is 0, and what is that? This is, well, minus the generalized Ricci tensor. So Ricci V plus is equal to 0. That's what we obtained. Now, I can write down some formula. Just okay, it's not so important. When we actually introduce a cutoff, so with a cutoff, the cutoff is that when we have those Z1 and Z2 that appear in that omega and therefore in the propagator, we say that whenever this distance between them, if it's less or less than equal than some prescribed length scale L, then we simply introduce the sharp cutoff, then we say, now it's 0. We do not allow these points, the Z1 and Z2, to get too close to each other. And this L might be a function of whatever, of the midpoint or something like that. So this is in principle a function on S2. So the cutoff might be like depending on where we are. Somewhere it might be shorter, somewhere it might be longer, whatever. And what we get, let me just write an expression. So when we take the one loop effective action, I will not write it like this one loop, I just say it. And with one cutoff, and epsilon times, and minus the same thing with another cutoff, effective a. What is epsilon? Epsilon will come, we'll take the limit, epsilon goes to 0, because we want to take the limit when cutoff goes to 0. So then this guy will depend on those two cutoffs, on L1 and L2. So it is as it should look like. So it is an integral over S2 of the logarithm of L1 divided by L2 and times something, times that's something which is called the Weil anomaly. So what is that something? It's like we take A just on the boundary, just the boundary value of our field. And we only take, first we take the part which contains, which is values in V plus, let's say. So this is a 0, 1 form. And we take the other guy who is 1, 0 form and has values in V minus. And then we have to contract those Lie indices. So this is values in V plus, and this is values in V minus. And how we contract those Lie indices? Well, using that diagram. It's the divergent term that appeared there. So it's, plus and minus. So this is the generalized Ricci tensor that we plug here, and we saturate one of its entries by A plus and the other one by A minus.
But is there a dilaton somewhere, or?
Here, there is no, it's happening on just for Chern-Simons. There is no place for any dilaton here.
Okay, so we are not yet at...
Yeah. And, okay, as I said
but I mean, at one loop, it is important maybe to include the dilaton for conformality, because otherwise...
So let me now try to kill this talk, because I have like 6 minutes maybe left, so let's deteriorate to the end. Okay. So this is what is happening. From there, from this Weil anomaly, it's not difficult to compute also the randomization group flow. So from that, finally, we get also the RG flow, which was something like that, d over, d epsilon in this case. That's V plus is equal to minus H V plus. That's what I was talking, I introduced kind of axiomatically before. Now one can compute it out of that stuff. But what now needs to be done? And it's sort of difficult to do it in 5 minutes. But let me still tell you something. If the same thing is done for arbitrary Courant algebroids, in particular, say for exact Courant algebroids where this is simply just two-dimensional sigma model, this boundary condition, right? So what we get thanks. So yeah, I will not now, okay, or let me now write maybe for a Courant sigma model, we have now really, there are more fields. I will just write kind of a little bit randomly. There is a parts of, if you choose a trivialization of this vector bundle or something like that, and even choose coordinates on the base, there will be a part that looks like fields from Chern-Simons theory. So the classical part would be like a one form, but then there would be a thing which corresponds to coordinates or to the point on the base, and there would be a part which corresponds to like momenta for the base, something like this. And now the propagator now looks slightly, or there is one more particle, so to say, is the thing which connects X and P. And finally, when we do the calculation, at least naively, what we get at the RG flow or the Weil anomaly is given precisely by this generalized Ricci tensor for our generalized metric, but let me draw it anyway. So there is this plus, minus, plus thingy, sorry, minus. So this is one divergent diagram, but there are now two more divergent diagrams. So one of them with one loop. So both of them have like this plus and minus, like this, and plus. And so here's this new thing. This is just binary vertex which corresponds to the anchor. So it becomes this new particle, which then differentiates this vertex. And there is a relative weight 1/2. So if one computes those divergence rates, then this comes with 1/2. And then there is minus 1/2, and the same kind of thing, but where this guy is rather minus. Just, yeah, there are two more divergent diagrams. Not surprising that there are more things, but this is exactly what was that. This is Ricci V plus, and for the divergence which is given by the constant volume form on the base. You see, like the base has to be put into, has to be seen as a vector space, or we need to choose coordinates on the base. So it's like a coordinate divergence. Okay, that's the calculation, but there are now many things that need to be understood. This divergence thingy, see, it was kind of randomly chosen. It depends on gauge fixing, roughly speaking, on the choice of coordinates, so to say, on the Courant algebroids. So one should understand why, how exactly is happening. It's happening that if you choose it differently, yeah, what's behind it? There is a related thing that here in this Courant model there is also a tadpole. There is a tadpole diagram that looks like there is this A thingy, but then okay, it can split off. It becomes like this vector field thing, and it can come back to itself and differentiate this stuff. That's a tadpole. Tadpoles pose problems, and this one is related to that divergence thing. So how one interprets that thing, it shows up in this divergence. It needs to be understood properly. What I'm saying is just kind of impression. Then next thing, as you were getting to it, dilaton. Yeah, so now we can also have somehow just a dilaton term. How to put it? So the boundary conditions that I have so far didn't come with a boundary term for the action. I didn't say it explicitly, but it's just like that. So you just take plain Courant sigma model action, impose the boundary condition, and you do not need to add any boundary term. It was just this. Also for this Chern-Simons thing, it was just this. But now with the dilaton, we would just put there some kind of dilaton term, so things that look like scalar curvature on sigma times some function which is on M.
On which basis you will use this? You will make this choice?
Yes, so the dilaton term, it should be an integral
Yeah, it's the Franken-Zeitlin term.
over sigma,
yes.
and there should be like scalar curvature of a metric on sigma. So this is a thing that now uses the cutoff. I mean, the metric on the sigma, it really depends on the cutoff, or cutoff gives us the scale which particular metric we choose, and times some dilaton thingy, which is which would be a function of this x.
Yeah, but you use this because you know it already, right? There is nothing in the theory that tells you that...
Okay, such things, I'm just saying that we don't do it because we don't properly understand it. But such things should appear there. There should be somehow two loop diagrams now appearing, apparently, if I understand things correctly. And there should be a good understanding of what is that generalized Laplacian. As I said, generalized Laplacian was a thing which depended only on the generalized metric and not on any divergence. And we don't know what this generalized Laplacian here is. And the final thing, where you started, I will just end my talk, that's supersymmetry. For that one has to start over how to get supersymmetric two-dimensional things. Somehow we can do it formally in some sense of those Ramon fields and things like that can be cooked up there in some artificial way, but for a good understanding, say, together with those boundary conditions and things like that we're lacking. We just don't know how to what should we do, say, with this Chern-Simons theory? What kind of super Chern-Simons theory we should choose and what kind of boundary conditions? Okay, that's the end. Thank you very much.
Okay, thank you, Pavol. Are there some questions in the lecture hall? Yes.
So you explained that this choice of E plus gives rise then to some boundary condition for this Courant sigma model. Mm-hmm. But for example, for Chern-Simons, does this give a way to give all possible boundary conditions I can put for Chern-Simons, or just these particular ones that you discussed, or how general is the framework? For example, for Chern-Simons.
Okay, well, one can say that the boundary condition that I wrote is the general conformally invariant boundary condition that one can write down. I mean, classically conformally invariant. So in that sense, it's a good class of boundary conditions. It's not a random class. I don't know whether it's not a true answer to your question. Because it's in some class of things that say only use the boundary values of that A and not any derivatives, for example, like that. And also it should be a condition which is linear in A. So if I take these two properties, that's condition which is just linear in A and only uses A and no derivatives, and I want it to be conformally invariant, then that's the only possible boundary condition that exists. And that's why this class is kind of maybe reasonable. And yet it's close with respect to at least one loop RG flow. So it's like a renormalizable class. But I don't know what would happen when we go to higher loops. There is a hope that it's good enough, but it's an open thing.
Okay, thank you.
Any other question in the room? Is there some online question? Let me ask a question also. So in Polczynski's book, there are a number of ways that the critical dimension for bosonic string is found. Is there some new insight maybe here about the critical dimension? What would it mean in your framework?
Do
you get that D equals 26 here?
Okay, the short answer is I have no idea. Slightly longer answer is that I still have no idea, but it's related to that Laplacian thingy, and that, let's say that, not yet here, but in that equation that I was writing, I think like this is equal to 0, and that should correspond to like being conformal with 0, whatever. What is it called? This, now I even forgot the word. The central charge, sorry. But in general, there is a number which I, of course, don't know because I always forget what it is, but roughly speaking, it's C times sigma is how the central charge should enter the game. And finally, when things are combined together in the right way, then this guy should be equal to 0. And so I don't know, like one would probably pick up sigma in such a way that is the smallest or largest, whatever eigenfunction of this Laplacian operator, and then we need to combine things together in such a way that this C vanishes. Yeah, so no new insight.